Okay. Okay. Good morning, students. So today we have lecture number 1 on electromagnetic induction. We are going to start a new chapter. Electromagnetic induction. Electromagnetic induction. Before this, we have studied. This is electromagnetic induction and alternating current. That is, these two are the last chapters of first part of the second year syllabus. Last chapters of first part of the second year syllabus. Okay. And before this, we have studied about the magnetic field, magnetic induction, other things I hope we have studied. So it is in the first chapter, that is electrostatics. We have studied that an electric charge produces electric field. An electric charge produces electric field. Now, an accelerating electric charge produces electric current. That also you have studied. An accelerated electric charge will produce electric current. Okay. So it is a charge produces electric current. Okay. And when electric current flows through a conductor, when a charge flows through a conductor, an electric current is produced. When electric current flows through a conductor, the magnetic field is produced. That we have already studied. When a charge flows through a conductor, electric current is produced, and when a electric current flows through a conductor, a magnetic field is produced. Now, the question is, now the reverse of that, that is, the question is, can moving magnet produce electric current? Can moving magnet or magnet produce electric current? Reverse of that. Electric current produces magnetic field. Okay. When electric current flows through a conductor, it will produce magnetic field. That magnetic field strength we have determined by using Biot-Savart's law, and all that things we have studied in the previous chapters. Now the question is whether a magnet can produce electric current or not. So that was invented. So that was the question in the during the development of the science. So now then two scientists by name Michael Faraday, and another scientist by name Joseph Henry, both independently conducted the experiment to check whether the magnet will produce electric current or not, and they succeeded independently. So Michael Faraday was from England and Joseph Henry was from USA. They separately, independently conducted the experiment to check whether the magnet produces electric current or not. And they observed that the changing magnetic field, the changing magnetic flux produces or induces an EMF. The changing magnetic flux induces an EMF and produces an induced current, and this phenomenon was called as electromagnetic induction. It is called as the electromagnetic induction. Once again, the changing magnetic flux associated with a conductor, the changing magnetic flux through a conductor or a circuit induces an EMF, or produces an EMF, and this induces an electric current. Induced current is produced, and this phenomenon is called as electromagnetic induction. Understood? And it was discovered by Michael Faraday and Joseph Henry. Okay. So before studying about this electromagnetic induction in detail about the experiments, so first understand what is magnetic flux. First you understand magnetic flux. Magnetic flux. You have studied about the electric flux. In the electrostatics, I hope you have studied about the electric flux, Gauss law. So now magnetic flux. The magnetic flux through a surface placed in a magnetic field is defined as the total number of magnetic lines of force. The total number of magnetic lines of force passing through that surface normally. The magnetic flux through a surface placed in a magnetic field. The magnetic flux through a surface placed in a magnetic field is defined as the total number of magnetic lines of force passing through that surface perpendicularly or normally. Understood? that is the total number of magnetic lines of force passing through a surface perpendicular to that surface, that is called as magnetic flux. It is called as magnetic flux. Understood? It is, let us consider, there is a uniform magnetic field. There is a uniform magnetic field. Uniform magnetic field is denoted by parallel lines, that is magnetic field lines. And now there is a surface. There is a surface area perpendicular to this uniform magnetic field. So there is a surface area A. This surface area is perpendicular to the magnetic field. So the magnetic field is perpendicular to the surface area. Then the magnetic flux linked with this coil or magnetic flux of this surface is given by, magnetic flux is given by vector, that is B into A, that is magnetic field into, that is magnetic field into area. See here, what is magnetic flux? First you understand. The magnetic flux through a surface placed in a magnetic field. The magnetic flux through a surface placed in a magnetic field is defined as the total number of magnetic lines, magnetic field lines which pass through that surface perpendicularly. Understood? The total number of magnetic lines of forces passing through the surface perpendicularly, that is called as magnetic flux. So now there is a uniform magnetic field. In that uniform magnetic field there is a surface. The area of the surface is A. Then magnetic flux through that surface is given by B into A. That is, so in general, so that is the magnetic flux is measured as, the magnetic flux is measured as the component of the magnetic field normal to the area. The component of the magnetic field normal, the product of the component of the magnetic field normal to the area. The magnetic flux through a surface is measured as the magnetic flux through a surface is measured as the component of the is measured as the product of component of the magnetic field perpendicular to the surface area and the area. Component of the magnetic field component of the magnetic field perpendicular to the area and the product at the surface area, that is called as a magnetic flux. So here once again I will tell you once again. So magnetic flux is measured as the product of component of the magnetic field perpendicular to the surface area and the area of surface. That is if the magnetic field is not perpendicular, let us consider that this is a uniform magnetic field. A magnetic field is there. And now the area is like this. Area is like this. Then the component of the magnetic field perpendicular to the area. The component of the magnetic field perpendicular to the area. That is, this is area and area vector. We know area vector is drawn perpendicular to the area. A straight line. That is a normal drawn to the area. That is, if this is area, then normal to that area is called as direction of that area, that is area vector. So along this area vector, if this is the area vector that is perpendicular drawn to the area, then this area vector makes an angle theta with the direction of the magnetic field. Then the component of the magnetic field along this area vector will be B cos theta. The component of the magnetic field along this area, along the perpendicular to the area, the component of the magnetic field perpendicular to the area will be B cos theta. So therefore magnetic flux is given by, magnetic flux through this surface is given by phi is equal to B cos theta into A. B cos theta into A, that is BA cos theta. BA cos theta, or you can write vector B dot vector A, that is dot product of magnetic field and area. Dot product of magnetic field and area, you can tell. See here, once again I will repeat. The magnetic flux through a surface is measured as is given by the magnetic flux through a surface is measured as the product of component of the magnetic field perpendicular to the area, component of the magnetic field perpendicular to the area and the area, surface area, and the product of component of the magnetic field perpendicular to the area and the surface area is called as magnetic flux. The component of the magnetic field perpendicular to the area is B cos theta, because this is area is not perpendicular to the magnetic field. If area is making, it is the normal drawn to the area makes an angle theta with the direction of magnetic field, then the component of the magnetic field normal to the area will be B cos theta, and that B cos theta into A will gives the magnetic flux, or you can write BA cos theta. So, BA cos theta. So, A can be also called as area vector. So, therefore, so you can write phi is equal to vector B dot vector A, that is dot product of magnetic field and area vector. Magnetic flux is defined as the dot product. Another definition, magnetic flux is defined as the dot product of magnetic field intensity and area vector. Understood? Okay. So, this is magnetic flux. Understood? So, now special case, now case number 1. So, now if theta is equal to 0 degree, that is magnetic field is parallel to area vector. If magnetic field is parallel to area vector, magnetic field is perpendicular to the area vector. Say here theta is equal to 0 degree. That means this normal is along the direction of the magnetic field. The normal drawn to the area is along the direction of the magnetic field. That is the area vector and magnetic field. The area vector and magnetic field both are in the same direction. That is magnetic field is perpendicular to area. Magnetic field is perpendicular to area. Theta is equal to 0 means parallel line. Magnetic field is perpendicular to area. Then what happens? Then magnetic flux phi is equal to BA cos theta, cos of 0 degree. Cos of 0 degree is 1. So, phi is equal to BA. Then this will be maximum. This will be the maximum magnetic flux. It is magnetic flux through a surface area will be maximum when the surface area is perpendicular to the magnetic field, or magnetic field is perpendicular to the surface area. If surface area and magnetic field are perpendicular to each other, then the magnetic flux will be maximum. Or if area vector is parallel to the magnetic field. Area vector means a normal drawn to the area. A normal drawn to the area. That normal drawn to the area, say this as n cap. Say this as n cap. If this n cap is in the direction of the magnetic field. If this n cap is in the direction of the magnetic field, so n cap is also here and magnetic field is also here, then theta will be equal to 0 degree. Then magnetic flux will be maximum. Or this area, if you take only area, the area has to be perpendicular to the magnetic field. Area, surface area has to be perpendicular to the magnetic field, then the magnetic flux will be maximum. Don't get confused here. Okay, next case number 2. Case number 2. If theta is equal to 90 degree, that is the normal drawn to the area, that is area vector. The normal drawn to the area, that is nothing but area vector. If area vector is perpendicular to the magnetic field, if area vector is perpendicular to the magnetic field, that means magnetic field is in this direction, and area vector is perpendicular to the magnetic field. It is area vector is like this. That means the area is surface area is parallel to the magnetic field. The surface area is parallel to the magnetic field. Magnetic field is parallel to surface area. Or area vector is perpendicular to magnetic field. Area vector is perpendicular to magnetic field. Then theta will be equal to 90 degree. Or if theta is equal to 90 degree, then magnetic field is parallel to surface area. Surface area is different, area vector is different. This is called surface area. Okay. This is called surface area, and area vector means a perpendicular drawn to this surface. A perpendicular drawn to this surface is called as area vector. That area vector, that is normal drawn to the surface, So, magnetic field is parallel to the surface area, or area vector is perpendicular to the magnetic field. And then phi is equal to BA cos of theta, that is cos of 90 degree. So, cos of 90 degree is 0, then phi will be equal to 0, that is magnetic flux will be 0. So, magnetic flux through a surface parallel to the magnetic field. The magnetic flux through a surface parallel to the magnetic field is 0, and magnetic flux will be maximum if the surface area is perpendicular to the magnetic field. If surface area is perpendicular to the magnetic field. Understood? Understand these 2 points? These 2 points are different. Okay. So now the understood the magnetic flux. It is magnetic flux through a surface is defined as the total number of magnetic lines of force passing through that surface perpendicularly or normally. Okay. So that is in general magnetic flux is given by the formula phi is equal to BA cos theta. Now what is the unit? The unit of magnetic flux is Weber. The SI unit of magnetic flux is Weber. The SI unit of magnetic flux is Weber. So, the magnetic flux is said to be 1 Weber. The magnetic flux is said to be 1 Weber if 1 Tesla of a uniform magnetic field. The magnetic flux through a surface is said to be 1 Weber when a magnetic field of 1 Tesla acts normally through a surface area of 1 meter square. When a magnetic field of 1 Tesla acts normally through a surface area of 1 meter square, then magnetic flux through that surface is said to be 1 Weber. Define 1 Weber, unit Weber. The magnetic flux through a surface is said to be 1 Weber or unit Weber when a magnetic field of 1 Tesla, acts normally through a surface area of 1 meter square, through a unit surface area or 1 meter square surface area, then the magnetic flux will be 1 Weber. Understood? So that is 1 Weber is equal to 1 Tesla meter square, 1 Tesla meter square. Understood? And this is SI unit of magnetic flux. And CGS unit of magnetic flux, is Maxwell. CGS unit of magnetic flux is Maxwell. SI unit is Weber. CGS unit of magnetic flux is Weber. So that is CGS unit of magnetic flux will be Maxwell. So now the magnetic flux is said to be 1 Maxwell. The magnetic flux through a surface is said to be 1 Maxwell. The magnetic flux through a surface is said to be 1 Maxwell if a magnetic field of 1 Gauss, acts perpendicular, if a magnetic field of 1 Gauss acts perpendicular to a surface area of 1 centimeter square, Gauss is the CGS unit of magnetic field. And centimeter square is the CGS unit of area. Understood? So therefore 1 Maxwell is equal to it is 1 Gauss centimeter square. Gauss is the CGS unit of magnetic field and centimeter square is the CGS unit of area. Understood? And now 1 Weber is equal to relation between Weber and Maxwell. How to write relation between Weber and Maxwell? So it is 1 Weber is equal to that is 1 Tesla into 1 meter square. 1 Tesla is equal to how many Gauss? 1 Tesla is equal to 10 to the power 4 Gauss. Right? 1 Tesla is equal to 10 to the power 4 Gauss, and 1 meter square is equal to how many centimeter square? So 10 to the power 4 centimeter square. So therefore 1 Weber is equal to 10 to the power 8 Gauss centimeter square. Gauss centimeter square. Or Gauss centimeter square is called as Maxwell. Gauss centimeter square. Gauss centimeter square is called as Maxwell. So 1 Weber is equal to 10 to the power 8 Maxwell. 1 Weber is equal to 10 to the power 8 Maxwell, or 1 Maxwell is equal to 10 to the power minus 8 Weber. Understood? So this is unit of magnetic flux. Okay. So now dimension of magnetic flux. How to write the dimension of magnetic flux? So the dimension of magnetic flux, it is phi is equal to B, BA cos theta. So cos theta is dimensionless, leave it. And B, how to write the magnetic field B? We know the formula, F is equal to QVB sin theta. You know this formula, F is equal to QVB sin theta. So therefore you can write B is equal to F divided by QE. Leave that sin theta and leave this cos theta. We want dimension. Trigonometry functions are dimensionless. Okay. So you can write phi is equal to B. B is F divided by Q into V into A. That is phi is equal to FA divided by QV, and F is force, A is area, Q is charge, V is velocity. So it is dimension of force, dimension of area, and dimension of charge. So charge can be done as current into time, right? Dimension of time and dimension of velocity. So it is dimension of flux. So dimension of flux is equal to dimension of force, m L T to the power minus 2, and dimension of area, L square, and dimension of current, just we write it as A. I will write it as A. Okay. And dimension of time is T, and dimension of velocity dimension L, T raised to minus 1. And now simplify this one. So phi is equal to, that is dimension of magnetic flux is equal to, so m is only 1, so m raised to 1. Okay. L raised to 1 is here, and L raised to 2, so L raised to 3, and here also L. So this L goes to numerator, L raised to 3 minus 1, 3 minus 1, 2. So L raised to 2, right? L raised to 2. Now T raised to minus 2, and this one is T raised to 1 and T raised to minus 1. T raised to 1, T raised to minus 1, T raised to 0. So T raised to 0, so only T raised to minus 2. Only T raised to minus 2. So next A. This A goes to numerator, you get A raised to minus 1. So this is the dimension of the magnetic flux. The dimension of the magnetic flux is m L square T to the power minus 2 A to the power minus 1. Understood? Okay. So the magnetic flux, you understood what is magnetic flux? So magnetic flux through a surface is defined as is given by the product of the component of the magnetic field perpendicular to the surface. Component of the magnetic field perpendicular to the surface and the surface area, that is called as magnetic field, or the magnetic flux, that is the, or also you can write it as magnetic flux is defined as the dot product of magnetic field and area vector. The dot product of magnetic field and area vector is called as magnetic flux. Thus if it is a dot product means magnetic flux is a vector quantity or scalar quantity. Magnetic flux will be a vector quantity or scalar quantity. The magnetic flux will be a scalar quantity. It is dot product of two vectors. So magnetic flux is a scalar quantity. Understood? Okay. This is about magnetic flux. You have to learn about magnetic flux because magnetic flux is used in this chapter everywhere. So hence I told about the magnetic flux. Okay. You might have already studied, but still we have to study once again, just because it is there in the syllabus. It is also mentioned in the syllabus. And one more thing, because of COVID-19, a new syllabus has been introduced. That is, a new syllabus has been given. and according to that new syllabus, this chapter, in this electromagnetic induction chapter, none of the things are deleted. So that is complete syllabus. How much syllabus was there in the previous year? Complete syllabus is there in this year also. Understood? Nothing is deleted from this chapter of electromagnetic induction. Understood? So many things are removed. Some of the concepts are removed from some other chapters. So from this electromagnetic induction, deleted portion is nil. Deleted portion is nil. So hence it is completely same as in the previous year. Previous year your senior students, how much they have learnt about electromagnetic induction, all that things you have to learn. Okay, for theory exam. Okay. So now we are talking about electromagnetic induction. So what is electromagnetic induction? It is electromagnetic induction is the phenomenon. Electromagnetic induction is the phenomenon in which an EMF is induced. An EMF is induced in the circuit or conductor because of the change in magnetic flux linked with the conductor. The electromagnetic induction is a phenomenon in which an EMF is induced in a circuit or conductor because of the change in the magnetic flux linked with the conductor or circuit. So due to induced EMF, an induced current flows through the circuit, and due to the induced EMF and induced current flows through the circuit or conductor. It is called electromagnetic induction, and this was discovered by who? That is Henry Joseph and Michael Faraday. Independently they have did the experiment and they have discovered that the magnetic field will produce us the electric current. So now, so that experiment, let us study the experiment to demonstrate electromagnetic induction. Experiment to demonstrate electromagnetic induction, that is EMI. Experiment to demonstrate electromagnetic induction. First one, magnet and coil experiment. First one, magnet and coil experiment. Magnet and coil experiment. Okay. So here, simple experiment. I will explain it in a very, very simple manner. So there is a coil. A coil connected with a sensitive galvanometer. A coil, say it as coil C. Coil C is connected to a sensitive galvanometer. You know about galvanometer? You know about galvanometer? What is galvanometer? What is the purpose of using galvanometer? What is galvanometer? A galvanometer is a device used to detect the presence of electric current in a circuit. A galvanometer is a device used to detect the presence of electric current in a circuit, and also can be used to measure the electric current of very, very small order. Electric current of very, very small order, or very, very small electric current can also be measured by galvanometer. Our galvanometer is used to detect whether current is there or not in a circuit, that is given by the galvanometer. Okay. So a coil is there, and the coil C is connected to a sensitive galvanometer, and a magnet, a bar magnet, a strong bar magnet is held near to the coil. Okay. So first, when the bar magnet and coil, both are stationary. When the bar magnet and coil both are stationary, the galvanometer shows no deflection. The galvanometer shows no deflection when the bar magnet and coil both are stationary. When the bar magnet and coil both are stationary, the galvanometer shows no deflection. Understood? That means when the bar magnet, this is a bar magnet, this bar magnet and coil both are stationary. It is, they are not at all moving. Then the galvanometer does not show deflection. When bar magnet is moved towards the coil, when a bar magnet is moved towards the coil, the galvanometer shows a deflection. When a bar magnet, when the north pole of the bar magnet, second point, first point, when bar magnet and coil both are stationary, galvanometer shows no deflection. Second point, when a north pole of the bar magnet is moved towards the coil. When a north pole of the bar magnet is moved towards the coil, the galvanometer shows a momentary deflection. The galvanometer shows a deflection, indicating the deflection in the galvanometer indicates that there is a flow of current. Understood? See here, when the bar magnet and coil both are stationary, there was no deflection in the galvanometer. That means no deflection means there is no current in the circuit when both are stationary. And now when the bar magnet is moved towards the coil, in the second point, when the bar magnet is moved towards the coil, the galvanometer shows a deflection. When the north pole of the bar magnet is moved towards the coil, the galvanometer shows a deflection, indicating the flow of current in the circuit, that is current flows in the circuit when the bar magnet, when the north pole of the bar magnet is moved. Next, third point, when the north pole of the bar magnet is moved away from the coil, first it is moved towards the coil. When the north pole of the bar magnet is moved away, it is moved here and it is moved away from the coil. When the north pole of the bar magnet is moved away from the coil, then the galvanometer shows the deflection. Galvanometer shows the deflection but in an opposite direction. Galvanometer shows the deflection but in an opposite direction, indicating the flow of current in opposite direction. When a north pole of the bar magnet is moved towards the coil, galvanometer shows a deflection in one direction, right? When a north pole of the bar magnet is moved away from the coil, the galvanometer shows a deflection in a opposite direction, indicating the flow of current in a opposite direction. Understood? Next point, fourth point, when a south pole of the bar magnet is moved towards the coil or moved away from the coil, similarly like north pole, then also galvanometer shows the deflection. But the deflection shown is exactly opposite to the previous one. That is exactly opposite when the north pole of the bar magnet was moved towards the coil. When the south pole of the bar magnet is moved towards the coil or moved away from the coil, the galvanometer shows the deflection exactly opposite to that when the north pole is moved towards the coil or moved away from the coil. Understood? So that is the fourth point. Understood? So from this is the experiment conducted. So now conclusion. What do you understand from this experiment? So conclusion. This is the experiment conducted. So what is the result or what is the identification? So that first, when a bar magnet and a coil both are rest, that is when there is no relative motion, between the bar magnet and coil, then current flowing through the circuit is zero. Then current is not produced, EMF is not induced, and induced current does not flow through the circuit. Okay, when the relative motion between the coil and bar magnet is zero, that is first conclusion. Then when the bar magnet is moved towards the coil, then there will be a change in the magnetic flux linked with the coil. That is, we know that the magnetic field lines are drawn around the bar magnet, and that magnetic field lines change as the bar magnet moves towards the coil. The number of magnetic field lines entering this coil will changes. So thus the magnetic flux linked with the coil will changes, and magnetic flux linked with the coil changes, and EMF is induced in the circuit, and that induced EMF will give rise to an induced current, and due to that induced current a deflection is produced in the galvanometer. Understood? That is, when there is a relative motion, between the bar magnet and coil, the magnetic lines of force crossing this coil or crossing this surface area. Just now I told about magnetic flux. The number of magnetic lines passing this surface area will changes. That is, magnetic flux linked with the coil will changes. So when the magnetic flux linked with the coil will changes, an EMF is induced in the circuit, and this induced EMF will give rise to the induced current. and this is called as electromagnetic induction. This is called as electromagnetic induction. Understood? That is, the magnet is producing, that is the magnetic field, the changing magnetic flux is producing the electric current. Changing magnetic flux is producing the electric current. Understood? This is called magnet and coil experiment. Magnet and coil experiment. Understood? Next, one more point. When the relative motion between the bar magnet and coil is faster, when the relative motion between the bar magnet and coil is faster, so the deflection produced is more. The deflection produced is more. It is also observed. When the relative motion between the bar magnet and coil is faster, the deflection produced will be more. So this is all about the magnet and coil experiment. They will ask in the theory exam for 3 marks. Explain magnet and coil experiment. So you can write a few points, 1-2 points, and this diagram and conclusion, or just you can write the conclusion depending upon the marks. Understood? Okay. So now from this experiment we concluded that when the magnetic flux associated with a coil, when the magnetic flux linked with a coil changes, an EMF is induced, and that induced EMF produces a current in the circuit, and due to that current the galvanometer shows the deflection. Understood? Okay. So now the induced current strength, the strength of the induced current depends upon the strength of the induced current depends upon the relative velocity, that is relative speed between the magnet and coil. The strength of the induced current, the strength of induced current, it is how much induced current is produced. Strength of induced current depends upon the strength of induced current depends upon the relative speed between the magnet and coil. First one, relative speed between the magnet and coil, and second one, power of the magnet, power of bar magnet, whether bar magnet is how strong the bar magnet. So that is relative speed between the magnet and coil. The strength of the induced current depends upon the relative speed between the magnet and coil, and the strength of the induced current depends upon the power of the bar magnet, and the third one is number of turns, number of turns in the coil. The strength of the induced current also depends upon the number of turns in the coil, and also fourth one, permeability of medium, permeability of medium inside the coil, permeability of the medium, permeability of the medium inside the coil. So these all are the factors on which the strength of induced current depends. Remember this. Understood? The strength of induced current depends upon the relative speed of the bar magnet and coil. The strength of induced current depends upon the power of the bar magnet, and the strength of induced current also depends upon the number of turns of the coil, and the strength of induced current also depends upon the permeability of the medium in the coil, permeability of the medium in the coil. So this is called a magnet and coil experiment. Understood? Okay. Next one. Next, another experiment is there, coil experiment. So now magnet and coil experiment. Now the magnet is replaced by coil. So coil experiment. Second experiment, this is coil experiment. Okay. I will explain in a very simple manner. We want to understand the phenomena, what is happening. That is what we want to understand, not the exact experiment. Okay. So there is a coil. It's called primary coil. This primary coil is connected to a battery and connected to a rheostat. Let us say it is connected to a rheostat also. Okay. Okay. And a plug key, and also a plug key. Battery, rheostat. I will use all the three. Okay, this is called a primary coil. It's called a primary coil, and there is another coil. another coil, it is connected to the galvanometer. This is secondary coil. Secondary coil. Okay. So now this is coil experiment. Okay. So first, here when a plug key is switched on or off, when plug key is switched on or off, the current through this circuit will changes, and then the galvanometer shows a deflection. When a plug key in the primary coil, the plug key in the primary coil is switched on or off. When the plug key in the primary coil is switched on or off, the galvanometer shows a deflection. Galvanometer shows a deflection, sudden deflection in one direction and then in another direction. Galvanometer shows a deflection. Okay. Next, when current in the primary coil is increased or decreased, when the current in the primary coil is increased or decreased by using a rheostat. Second point, when the current in the primary coil is increased or decreased by using the rheostat, then also the galvanometer shows the deflection. Then also the galvanometer shows the deflection. See here. First point, when the plug key in the primary coil is switched on or off, then the galvanometer shows the deflection. The galvanometer in the secondary coil, will shows the deflection. Understood? When the plug key in the primary coil is switched on or off, then the galvanometer in the secondary coil will shows the deflection. Second point, when the current in the primary coil is increased or decreased, there is a battery, there will be a current. Okay. When the current in the primary coil is increased or decreased by using a rheostat, then the galvanometer present in the secondary coil will also shows the deflection. Third point. When current in the primary coil is maintained constant, that is, current is neither increasing nor decreasing. When the current in the primary coil is maintained constant, then galvanometer in the secondary coil does not shows the deflection. When the current in the primary coil is maintained constant, the galvanometer in the secondary coil does not shows the deflection. Understood? So this was the experiment conducted. This experiment is called a coil experiment. So now what is the conclusion? This much is enough. So what is the conclusion? Now conclusion of this experiment. Conclusion. First I will start from the third point only. Okay. Third point. In the third point, what we observe? We observe that when the current flowing through the primary coil is constant, that is neither increasing nor decreasing, then galvanometer shows zero deflection. That means when the current is uniform, the magnetic field or magnetic flux associated with the coil will be constant. The magnetic field or magnetic flux associated with the coil will be constant. As a result, magnetic flux is not changing, so induced EMF will not be there. So EMF is induced in the secondary coil. Only when there is a change in the magnetic flux. But when the current is constant, the magnetic flux linked with the coils, will remain constant. Hence, the galvanometer does not show the deflection. Understood? And next, when the current in the primary coil is increased or decreased, when the strength of the current in the primary coil is increased or decreased by using rheostat or by using a plug key, that is switching on means suddenly increasing the current. Switching on means suddenly increasing the current. Switching off means suddenly decreasing the strength of current in this coil. Understood? Switching on and off means increasing and decreasing the current in the coil, and increasing and decreasing the current in the coil can also be done by rheostat. So when the current in the primary coil is increased or decreased, then the magnetic flux linked with the coils the magnetic flux linked with the coil will also increases or decreases. That is, there will be a change in the magnetic flux. So the change in the magnetic flux induces an EMF, hence the galvanometer shows the deflection. So galvanometer shows the deflection only when the current in the primary coil will changes. The galvanometer present in the secondary coil will shows the deflection only when the current present in the primary coil will changes, because when the current changes, the magnetic flux linked with the coil will changes. So when magnetic flux changes, then the induced EMF is produced, and due to that induced EMF an electric current is produced, and electric current produces, then the galvanometer shows the deflection. Understood? Understand the complete relation. Understand the complete relation. That means constant current. If the current is constant, there will be a magnetic field, there will be a magnetic flux. A current flowing through a conductor produces magnetic field, and magnetic field means magnetic flux will be there. So because there is a surface area, magnetic flux will be there, and magnetic flux is constant. Magnetic flux is neither increasing nor decreasing when the current is constant. Then a galvanometer does not shows the deflection. That means galvanometer shows deflection, that is only when the magnetic flux changes. So that is electromagnetic induction. So what is electromagnetic induction? So electromagnetic induction is the phenomenon of inducing. The electromagnetic induction is the phenomenon of in which an EMF is induced in a coil. The electromagnetic induction is the phenomenon in which an EMF is induced in a coil because of change in a magnetic flux linked with the coil. Because of change in a magnetic flux linked with the coil. And this induced EMF induces an electric current. This induced EMF induces an electric current in the coil. Understood? So this is called electromagnetic induction. Introduction, magnetic flux, and these two experiments, that is magnet and coil experiment and coil experiment. These experiments will be asked for 3 marks. Explain coil experiment, or explain this is experimented to demonstrate electromagnetic induction. Either you can explain coil experiment, or you can explain magnet and coil experiment. Understood? So these experiments were conducted by Michael Faraday and Henry Joseph. They conducted the experiment and they discovered that the magnetic field, the changing magnetic flux produces an electric current. Understood? Okay. So next concept we will continue in the next classes.